Hi everyone and welcome back. In this video, we're going to talk about the system design of the distributed priority queue. Two use cases. The first one is ability to schedule a job at a specific time in the future. And the second one is ability to execute a job based on the priority. In this video, we're going to talk about two different implementation. The first one is based on the sharded SQL database, and the other one is based on the Redis. With this, let's get to the video. Before we talk about the system design, let's briefly go through the API and the schema of the item. So as you can see here, the API would consist of 5 simple methods probably. One would be enqueue an item. This is where we would put an item in the priority queue. Then we would want to dequeue the item, get it out of the queue. And as we consume a message from the queue, we would need to either ACK it, tell the queue that the message was successfully processed and can be removed from the queue, or we would need to NACK it. NACK means that the message was not processed correctly and we would want to retry to process it again, which means that the message is not removed from the queue, it stays in the queue, and then it would be consumed by another worker. And the other method is probably get some active topics that we have on our queue. Now, as we talk about the item schema, we have a queue and we have a producer of the queue or a service that sends a message to the queue and the consumer. So when a producer sends a message, we would need to make sure that we specify the following fields. We would need to have a namespace. It can create a clear separation of the different use cases or departments. Then in every single namespace, we can have multiple topics. And topic would represent a logical priority queue. In our case, it would be backed either by SQL database or a Redis that we're going to touch base later. Then every message has to have a priority, and we would represent that priority as an integer number and then sort all the items inside our queue by that priority. Then we have a payload, which is an actual message that producer wants to send. And this message can be simply encoded into the byte array and sent as a blob. Then we have a metadata that likely would be represented as a key value. It can be used for multiple purposes. We, for instance, might be clearing the key value metadata to be able to retrieve specific type of messages in the queue, or we can use it to create an exclusive queue. Metadata gives us opportunity to create multiple features and make the consumption of the messages more sophisticated based on different criteria. The next attribute is deliver after or a delay. So as a producer posts a message to our queue, one can specify when that message can be consumed. For instance, it can be consumed 1 week from now. So until then, our message would stay in the queue and be invisible. It wouldn't be consumed until the date is current. The next one is lease duration. Lease means that the queue allows the message to be processed for a specific amount of time. For instance, if the lease is 1 second, it means that the consumer has only 1 second to process the message and acknowledge the consumption. If consumer can't process the message in 1 second, then the message would be retried and stay inside the queue. This is a protection against the consumer crashing, because if the consumer received the message and then crashed in the middle, we don't want that message to be lost. So if it's not processed in 1 second, then that message would be retried again by a different consumer. The next one is a unique ID. This is an ID that likely we would want to assign to every single item, and it would specify the location of the data in our database or in our Redis. And since we're going to shard the databases, so ideally for our unique ID, we would need a shard ID to be able to find the shard of the database and then the primary key of the database to be able to find a specific row inside that shard. And the last one is time to leave. Time to leave has to be assigned to a message, just so if it's not consumed over the specific amount of time, the message gets dropped or sent to a dead letter queue, because we don't want messages to be pushed to the queue and then stay there forever. If they're not consumed over the specific amount of time, they have to be pushed to either dead letter queue or dropped from the queue. Now let's look at the high-level representation of the queue. And as you can see on this diagram, we would have 3 components. We would have an application that would enqueue the message or push the message to our queue. Then we have a priority queue that would maintain a sorted by priority list of messages, and then consumers on the right side would be consuming messages based on the priority. So the lower the integer number, the higher the priority, which means that messages with the priority 1 would be consumed first. We said that some of our messages can be posted in the future, and until then they have to be invisible. It means that we need to sort our items by 2 fields. The first one would be a timestamp, a numeric value, and the second one would be a priority. Now let's talk about how we're going to store our items in SQL sharded database. For every single topic, we would have multiple Enqueue workers that would be responsible for storing messages on the different shards. So let's say I post a message to the topic 1 of the queue service. That topic is backed by multiple shards of the MySQL database. And for every single shard, we would have an in-queue worker, which means that it would be listening to the incoming messages and then store them in the shard. To simplify the process, we can say that every single topic would end up on the single shard and it would not be distributed across multiple shards. But in this case, we might end up with a celebrity problem where some of the topic become very heavy and would overload the specific shard and keep other shards not in use. So ideally, we have multiple shards allocated for the specific topic and responsible for storing messages. To summarize the publishing process, it would look like this. We would send a message to a specific topic. That topic would have an in-queue buffer backed by multiple in-queue workers that would be responsible for storing those messages in their specific shards. So we would have one-to-many relationship between the buffer and workers, and every single worker would have one-to-one relationship to the shard, which means that there would be one worker per shard. As the message gets stored to one of our shards, it gets assigned a unique ID that will consist of the shard ID and the primary ID of the row inside the shard. Now, as we are trying to consume the message or dequeue the message, we would send a dequeue API call, as you can see at the bottom. And here we need to receive messages that have to be delivered now and have the highest priority. Prefetch buffer would use a dequeue workers to communicate with the shards and retrieve the messages that have to be delivered at this time was the highest priority. As we get those messages from the shards, we would then just do a simple k-way sort on those messages and maintain a priority queue in the buffer. That priority queue would be represented by a heap data structure and be able to serve a real-time consume requests. For the prefetch buffer to be able to receive and sort items from all the shards in the real time, we need to make sure that those queries are very lightweight. To do that, we would have a dequeue worker on the shard that would be responsible for running select queries on our tables for every single topic and retrieve the IDs of the messages that are ready to be delivered right now and have high priority. So to summarize, every single shard would need to maintain an index of items on the node, and dequeue worker would be querying the database every, let's say, second to retrieve and reindex all the items that are now available to be served. To improve the SQL query, we can use a checkpoint mechanism where every single time we query database, we set a new checkpoint. And the next time we query database, we would only retrieve items for the specific second instead of scanning through all the items. So our query would be, let's say, select all the jobs where the checkpoint larger than the previous time we query the database and less than the current time. This way we can reduce the load on the database. At the same time, as we maintain that index and store all those items ready to be queried, prefetch buffer would send requests to the dequeue workers and receive items that are ready to be served for the specific topic. Those items would be added to a heap that would be stored in the buffer inside the memory. Then the messages would be dequeued from the heap buffer. And as we keep dequeuing those items from the heap, we would keep sending requests to dequeue workers to be able to find more items to serve. Now, as the message is consumed, it's not over yet. It means that this is when the least time starts, which means that consumer, for instance, has 1 or 2 seconds to fulfill the request and send back either ACK of the message or NACK. If consumer sends ACK, it means that message successfully processed and it will be dropped from the queue. And if the consumer sends NACK, it means that the message was not processed as expected and has to be retried. This way, we can support 2 types of semantics. We can support at least one delivery and at most one. With at least one delivery, as the consumer gets the message, we need to wait until it finishes processing. And only when the processing is successful, we submit the acknowledgement. And if we want to support at most one delivery, then as the message is consumed by a consumer, we need to send acknowledgement immediately, which means that the message will never be retried. And then if we process successfully, it's going to be processed only once. And if it fails, then the message is going to be lost. That's why it's called at most one, which means either one or not processed at all. We spoke before that every single message would need to have a unique ID that would consist of the shard and the primary key. This ID would be used when the consumer sends an acknowledgement, for instance, because when that request is sent, the queue has to know where that message is located. So it's going to use the shard ID and the primary key to find the source of that message in the database and then update the status of the database. At the same time, if the consumer crashes and the lease expires, then our background processes on the shards would identify that for the specific message that was in process, the lease is over, and that message will be moved back to the original state and retried again for delivery. As the consumers send a API call to ACK or NACK, the request, we would have two types of buffers. We would have an ACK buffer and NACK buffer. And for every single buffer, we would have a separate workers assigned to it. So for acknowledgement, for instance, we would have a worker that would consume that message from the buffer and then go and update the state of the message in our shard, saying that the message consumption is completed. And for the NACK buffer, we would have a NACK worker that would do the same, but mark the state as pending for delivery. To summarize the design, it would look something like this. We would have a client that would send a request to one of our queues. Then every single queue host would maintain an API. It would have in-memory buffers for ACKing and NACKing, as we discussed before, and it would have database workers. Those database workers would be responsible for querying shards of the database and retrieving or updating the items inside the queue. We would also need to use a shard manager that would be responsible for maintaining the replication levels and mapping between the queues and the shards. So instead of every single queue maintaining it internally, we can just have a shard manager that would maintain that mapping inside it. Now let's talk about the reliability. The design that we just went through would be applicable for a single region design where we would just deploy a queue and shards in the same region and then provide low latency and between the shards and queue services, so the performance should be really fast. And it would look something like this, where we would have multiple regions that would be maintaining different types of data and responsible for different shards. This approach works, for instance, if we have 3 regions in the United States and our services always assigned to the specific region. But the problem here, if the region goes down, then we lose the data. And the only way for us to recover is to manually reconfigure and reconnect to a second region. It can actually be automated, so the failover can be automated on the client side, but every single client would need to implement that failover. At the same time, we lose in-flight data or data that would be scheduled for the future. For instance, in this case, if the region 1 goes down, all the messages that would be scheduled for the future would also be unavailable because the queue service is unavailable. So we got two problems. The first one is that clients would need to automate the failover logic inside their services, and that would be spread out across all the clients. And the second problem is that we would lose access to the shards if the specific region goes down. So the first one can be solved by putting a routing service in front of the regional queue services. So as you can see in this diagram, the client would communicate to the routing service that would know about the status of the regional queue services. This would allow also client to be able to specify the information about the routing or storing of the messages. For instance, client can say, I prefer my messages to be stored in region 1 or region 2, and the routing service would do best effort to do that. And if client doesn't specify anything, then the routing service would just send those requests or assigned a specific region for the client that would be the closest. So this solves the automatic failover issue that we have. To fix the isolated shard problem, we need to do two things. The first one, we need to make sure that every single shard has cross-regional replication. So in case region goes down, we still have access to a replica of data. And in our case, queue service 2 can connect to those replicas that now become masters. And the second one is that our routing service has to have knowledge about the queues, topics, and shards and how they map between each other. For that, we would be using the shard manager to learn about mappings between the queues and shards. And we would also need to know the mappings between the topic and the queues. This way, as the client tries to push or consume a message, first we would send the call to the routing service to receive an address of the queue that we want to be connected to. So all the messages that we publish and consumed would go to the specific queue in the specific region. And if that queue becomes unavailable, we would need routing service to tell us what queue took over the old one and has access to the replicas. In our case, let's say client was using a queue service 1 for publishing and reading messages, and queue service 1 became unavailable. So queue service 2 now is the owner of the shard 1 and shard 2. So as that happens, we need to make sure that the routing service is updated with the knowledge about the shards. And as the client tries to resend or retry consumption from the queue, one gets access to shard 1 and shard 2 through the queue service 2. The second implementation is from Netflix, and they've built a priority queue on top of the Redis. They use Redis sorted sets to sort the items in the priority queue. I talk about this implementation in my course on system design that you can check out on my website. And this is it for the video. If you found it useful, make sure you like and subscribe, and I'll see you in the next one. Bye.